In this video, we will learn how to apply uh, physics to circular motion to be able to understand things such as banking angles for racetracks or roller coasters, or the speed necessary to complete a vertical loop, um, and among other things. We need to remember that acceleration is not just a change in speed, that acceleration is technically a change in velocity, which is a change in speed or a change in direction. When we look at something that's going around in a circular path, we need to remember that if I have this ball and it's going around in a circle, right now its velocity is tangential to the circle, so it's going up and to the left. As the ball moves a little bit further along, the velocity of the ball, while the magnitude, the length of the arrow will stay the same, the direction of the arrow will change with each moment of time as it goes in a different direction. And so the acceleration of this ball can be thought as the difference between which way it was heading initially and the way that it is heading now, or the vector that gets us between those two. And I don't think I drew those correctly, but I think I drew this arrow too long because it really should be pointed, inwards more. So anyways, the acceleration in order to change our speed is always going to be inwards. So to go from here, from at that moment to the next, it's going to be pointed inwards towards the center. So again, velocity is tangential to the path that you're taking in a circle. Acceleration is always going to be in towards the center. And the centripetal, not centrifugal, that's a made-up force, but the centripetal force is also inward. Some important formulas that we need to know for dealing with circular motion is first how to find the velocity. The velocity of an object moving a circular path is equal to 2 pi r, r for the radius, divided by t, which is the period, the time it takes to go around the circle. If you think about it, 2 pi r is just equal to the circumference of the circle. So it's a distance, the distance around the circle, and the t is the time it takes to go around the circle. So we're taking the distance divided by the time, and that's how we get speed. Acceleration can be shown by some math to be equal then to the speed squared divided by the period that it takes to go around. Or if we substitute in the formula for v into this acceleration equation, we can also put this centripetal acceleration in terms of the radius and the period, as seen here. So these three formulas will be very useful in doing circular motion problems. So let's just look at some example problems. Again, there's not too many new formulas here, so that's why we're diving right into example problems. Here we have a really studly example of a man spinning a 1 kilogram mass around his head, and we want to know how much force is he going to have to use with his super buff muscles to be able to keep this object in a circular path. So it's a 1 kilogram mass. It's moving in a circle that has a radius of 1 meter. He times how long it takes to spin around 5 times, and it takes 12 seconds. So the first thing we need to know is what is the actual period. So we take 12 seconds divided by 5 revolutions to find that it takes 2.4 seconds for every revolution. We plug this into our formula for acceleration. Acceleration equals 4 pi squared times the radius, 1 meter, divided by the period, 2.4 seconds squared, and we get an answer 6.8 meters per second squared. We now take that acceleration and plug it into F equals ma, so force equals mass, 1 kilogram times 6.8 meters per second squared, and we get 6.8 newtons. So again, the only force on this object is the force of the string, and so the net force and the force that we found are the same at 6.8 newtons. Another problem that we could be interested in looking at is when an object goes around in a circle, such as a roller coaster, in a vertical circle, we want to know how fast you need to go in order to not fall out at the top. So of course, when you're riding a real roller coaster, there are safety mechanisms. So if the roller coaster gets stuck, you're not going to fall out of the cart, and the roller coaster can't fall off the track because there's something to hold it on. But let's say, well, what if you didn't have those? How fast would you need to be going to stay on the track? The first thing we need to realize is that if the slowest you could go, and you can obviously go faster, but the slowest you need to go is to make sure that when you're at the top, the rate you would be falling at is equal to the rate that you would normally fall at anyways, free fall. So your acceleration would have to be 9.8 meters per second squared. If you're going any slower than this, you would fall faster than the track is curving around, and you would fall out of your seat. If you're going faster than that, then the track has to pull you around faster than you would fall, and so you'd be actually pushed into your seat. So if we set our centripetal acceleration at the top, and remember centripetal acceleration is this formula, if we set that centripetal acceleration to 9.8 meters per second squared, and then plug in 5 meters for our radius, since the diameter was 10 meters, we can find out how fast we need to be going in order to not fall out. And when we solve for v, we get 7 meters per second. Now again, this is the slowest we could go and not fall out of our seats. If we went faster than this, it would actually feel like we're being pressed into our seats up at the top. When you're down at the bottom, now because you would feel double that force, double your normal force, because now at the bottom, if you take a look at what's going on, you've got let's make sure I'm still on an arrow, I believe I am. At the bottom of this, you have your weight is going down. Your normal force has to be twice as great as your weight. In this case, assuming you're going the same speed at the top as at the bottom, which of course you're not, you're going faster at the bottom than at the top, since you've accelerated on the way down. But let's say you are going the same speed, your normal force has to not only counteract the weight, but it also has to provide the centripetal force upwards, and so you would feel like you are at double your normal weight at the bottom of this. Moving on to another problem, sometimes it's useful to know what angle you should bank a corner at if you don't want to ever have to worry about something sliding off. So if you think of like a NASCAR track, the corners are banked. This way we don't have to rely on friction between, or at least as much depending on what the banking angle is, friction between the tires and the road surface to move the car around in a corner, but rather the normal force, the car pushing down on the road, is what provides this force. So if you look at a car going around an angle, it has two forces, a banked track. It has two forces on it, the weight pulling down, of course, and then the normal force. If we look at the normal force, we can think of it as broken into two different components. There's the vertical component of the normal force, which has to counteract the weight so that the car does not accelerate in the up or down direction. There's also a horizontal component of the normal force, and that's what provides the centripetal acceleration, the centripetal force to get the car around the corner. So looking at those two forces, or those two directions, vertical and horizontal, again, the horizontal force, the net force in the horizontal direction is equal to only the horizontal component of the normal force, and so that's equal to the mass times the centripetal acceleration from Newton's second law. In the vertical direction, we have the vertical portion of the normal minus the weight, okay, because those are the two in the vertical direction, and that has to equal 0 since the car is not accelerating vertically. We can find then the centripetal acceleration is equal to v squared r. If we plug in the numbers from the problem, we find that the normal force, the horizontal portion anyways, must be equal to whatever the mass of the car is. We'll find out this doesn't matter, times 4.5 times 4.5 meters per second squared. In the vertical direction, the vertical part of the normal is equal to the weight, which equals mass times 9.8 meters per second squared, because remember, weight equals mass times g. And then we find that the angle then So the angle that it has to be banked at is equal to the same angle um, that we used to break the normal force vector into its component forces. That angle is equal to the inverse tangent of the horizontal component of the normal divided by the vertical component of the normal. So that's equal to, if we take a ratio of these two, mass cancels out because it's both on top and the bottom. So I have 4.5 divided by 9.8. And if I solve this, I get 25 degrees. So a 25-degree banking angle will provide for any car, because mass cancels out, the proper amount of force for a car going 30 meters per second if the radius of the turn is 200 meters. If the car is going faster than that, then you'll need to rely on friction on the road surface to keep it sliding. And so you could do problems where you look at how much friction would there be if it was going 40 meters per second instead of 30. If it was going slower than that, 30 meters per second, you'd actually have to rely on friction to keep it from sliding downwards into the center of the curve. And, again, assuming there's enough friction, that either way it would work out. So those are a few example problems. We'll work a couple more in class. So the problems we'll look at in class is how strong does Spider-Man's web need to be for him to be able to perform some of the feats, such as jumping off a tall building, grabbing Mary Jane, and then swinging to safety. So we'll take a look at that in class. We'll also take a look at in class how fast does the puker need to go in order to kind of cement you up against the side walls there and make it so that you feel like you're really pressed against and you're not going to slide down the walls. Okay, so those are what we'll be looking at in class.